Hey everybody, we're going to have our intro video to applied linear algebra. Most of this we're going to start out, we're going to have some definitions, some examples, and when we get to the examples, I'll do my best to go slow, cover them step by step. There will be some videos mixed in with these lecture videos of how to use your graphing calculator to simplify matrices, augmented matrices. But anyway, let's go ahead and get started. And I'm just going to start up here. A system of linear equations has three characteristics, three outcomes, no solution, exactly one solution, or infinitely many solutions. The bottom two, if there is a solution, whether it's exactly one or infinitely many, is considered a consistent system of linear equations. If there's no solution at all, we're going to call it inconsistent. Now, what you're familiar with from the past in college algebra, where you solved a system of equations, would have been where the point where two lines intersect one another, even up and towards calculus, where you might have had a parabola and a line. If they intersected once or twice, then you were able to set those equal and find those intersection points. If you had two lines that were parallel and never intersected, then you had an inconsistent system, which was the first case. All right, so an example of a system of equations would be x1 minus 2x2 plus x3 equals 0. Now this system has three equations with three unknowns. The second equation is 2x2 minus 8x cubed equals 8. And the third equation is 5x1 minus 5x3 equals 10. x1, x2, and x3 can represent vectors. And that's kind of the venue or idea we're going to look at now in linear algebra. For that particular system, if you were asked to write a coefficient matrix, you would only worry about the coefficients of the variable side, 1, 0, and 5. The coefficients of x2 are negative 2, 2, and 0. And the coefficients of x3 are 1, negative 8, and negative 5. So each column represents the coefficients of each of the three variables above. If you're asked to write an augmented matrix, it is the coefficient matrix with the column of the numerical values from the original system as your last column. These systems, or matrices, once converted, can be solved by elementary row operations. Now, early in the class, I will go through how to solve these systems using the elementary row operations, but also I'm going to put some videos up in your YouTube channel where we can just do it with the graphing calculator, and it'll save a lot of time. And that way you can also focus on the concepts of the class as well. Okay, so one elementary row operation is you can replace one row by the sum of itself and a multiple of another row. You can interchange two rows. And you can also multiply all entries in a row by a non-zero constant, like multiply by 3 or multiply by negative 2, whatever you like. And these three steps are very important when we're solving. Okay, so we're going to solve a system of equations by using elementary row operations. Okay, so system 1, we have 3x1 plus 6x2 equals 18. 3, 6, 18. The second equation is 4x1 plus 7x2 equals 26. 4, 7, 26. If any of those numbers are negative, you will include the negative with the number. Okay, So here's the multiplying by a non-zero value. The idea is you start in the lower left column of your matrix, and this is an augmented matrix because it includes the 18 and 26. In order to make this bottom left location a 0, now this doesn't have to be the way you do it, but this is a way to do it. 4 times row 1 minus 3 times row 2. Now when I do a row operation, I write the operation that I'm doing on top, and the answer to that operation I put on the bottom. So 4 times 3 minus 3 times 4, that's 12 minus 12 gives me 0. And again, this is where I'm putting the answers, row 2. Now, you can address each row separately. It doesn't always have to involve both rows. For example, I can take 1/3 of row 1. All of these numbers are multiples of 3, so I can multiply all of them by 1/3. 3 times 1/3, 1/3 times 6, and 1/3 times 18. I can also choose to reduce row 2 because it is also multiples of 3. 1/3 times 0, 1/3 times 3, 1/3 times -6. Translating this back after you've got your lower left position at a 0, this is 1x2 equals -2. 1x2 equals -2. Top row we have 1x1 plus 2x2 equals 6. So you can translate a row-reduced matrix back to your system. And by row reducing and creating a 0 in the bottom left, you have now solved for one of your variables. x2 equals -2. And then if you sub that in, x1 plus 2 times -2, which is x minus 4 equals 6, add 4 to both sides, and you get 10. So your solution is x1 comma x2. For this particular system, that's 10, -2. If you were to graph the equations from the original system, pretending you had x, y, then it would fall back to like college algebra where this would be the intersection point of the two lines. Once you've moved up to a third variable, 3 equations, I'm going to write this as an augmented matrix. The x1, those coefficients are 1, 2, 0, 1, 2, 0. The x2 variable, 0, 4, 2, 0, 4, 2. And then finally your x3s, it's -3, 7, 3, -3, 7, and 3. And then augmented means include your constants, 14, -3, -5. We already have a 0 at the bottom left position, but because we now have 3 equations, 3 unknowns, we want to make zeros here and here, essentially making a triangle of zeros. Let's concentrate on making this a 0. If I double the top row and subtract the second row, double the top row minus the second row, 2 times 1 minus 2, that's 0. And again, whatever I write under the arrow, that's the location of the answer that we get. 2 times 0 minus 4 is -4. 2 times -3 minus 7, -6 minus 7, that's -13. 2 times 14 minus -3, what is that? 28 plus 3 is 31. We've created a 0. Now, in order to get the bottom left triangle to be all zeros, we got to make this 2 go away. So let's be clever. What if we take row 2 and add 2 times row 3? 0 plus 2 times 0, and again, we're going to put our answers in row 3 because we want to have that diagonal of zeros. 0 plus 2 times 0 is 0. Negative 4 plus 2 times 2, that's negative 4 plus 4, that's 0. Mission accomplished. Negative 13 plus 2 times 3, negative 13 plus 6, that's negative 7. And then finally, 31 plus 2 times negative 5, 31 minus 10 is 21. Then, once you've created the diagonal of zeros, you start at the bottom row. Negative 7x sub 3 equals 21. Divide both sides by negative 7. x3 is negative 3. Then what you do is you work your way back up. Row 2, we have negative 4x sub 2 minus 13 x sub 3, but we can substitute the negative 3 in now, equals 31. That gives us negative 4x sub 2, or I'm just going to say x2 instead of sub all the time, plus 39 here. What's 31 minus 39? That's right, it's negative 8. Divide both sides by negative 4, and your x2 is 2. Finally, go to the top row of your row-reduced matrix. 1x1 plus 0x2 minus 3x3 equals 14. That's going to go to 0. That becomes positive 9. So 14 minus 9 is 5. And then you put everything in order, and you have 5, 2, negative 3. That ordered triple is the solution to this equation. If you replaced x1, x2, x3 with these 3 values and solve, each one of them will come out to these 3 values.